Greetings and welcome to Precalculus Polynomials and Rational Functions. In this lesson, we're going to focus on polynomial functions. Okay, a typical polynomial will look like this. It will be in this format. F of x. Now, all of the a with these little subscripts just go along with the x powers, just so we can keep them, but it's just a value in front of the x with the power. Now our polynomial could be any value of n. So if this was 10, this would just be a with a subscript of 10, x to the 10th power. The next one would be a to the subscript of 9, x to the 9th power, all the way down to a with the subscript of 2, x squared, plus a with the subscript of 1, x, and a to the subscript of 0. Now, these little subscripts are just naming these values, but it could have been 3, -2, 5, 7. They're just real numbers. But the important part is we're not limited to just x squared. It could be x to any power. We do want this first value, this a with the subscript of n, not to be 0. Then if it is not 0, then this first term is what's called our leading term. A with the subscript of n, x to the n power is our leading term. Our leading coefficient is the a with the subscript of n, and our a with the subscript of 0 is our constant term. It's just a number. Here are some common properties of polynomial functions. First of all, the domain of a polynomial function is the set of all real numbers, meaning it goes from -infinity to +infinity. If you have a function that has any limits on its domain, where it's only a subset of this whole real number line, then it is not a polynomial function. It must meet this criteria to be a polynomial function. Secondly, the graph of this polynomial function is continuous and smooth curve. It's continuous and it's a smooth curve. That's very important too. All right, so let's look at some possibilities. We have a function that's graphed in this kind of side S shape. We have a function that we hit a point and then there's a gap and we pick up our graph again. We have a graph that kind of hits a corner, bounces off, and then hits what's called a cusp and bounces off, like a bouncing ball or a slinky. The first one is indeed smooth. There's no sharp points, and it's continuous. There's no breaks, and therefore, this is a polynomial function. And in fact, it goes off to infinity both directions, and therefore, that's a polynomial function. The second one, it's not continuous, and therefore, it's not a polynomial function. The third one is not a smooth curve, and therefore, not a smooth curve polynomial function. You must hit these two criteria for us to have a polynomial function. The domain must go from -infinity to +infinity, which this does. This does too, and well, with a small gap, and this one does, but the problem is it's not continuous and smooth for these other two. Let's look at an example of our polynomial functions. First of all, we want to find the degree, the leading term, and the leading coefficient of the following functions. F of x equals 5x to the 4th minus 2x plus 7. And g of x equals 7x squared minus x plus 1, where our x value could be 1 is less than or equal to x is less than or equal to 5. Let's take a look at the solution for A. First of all, our degree is 4. It is the highest power that x is. So our degree is 4. Our leading term is the one what's connected to the x to the 4th, which is 5x to the 4th is our leading term, and our leading coefficient is 5. Now our solution for the second one g of x equals 7x squared minus x plus 1, and 1 is less than or equal to x is less than or equal to 5. Well, degree of freedom doesn't exist. Leading term doesn't exist. Leading coefficient doesn't exist. Now you might be asking, why in the world are you saying doesn't exist? Well, look at our domain. Our domain only goes from 1 to 5, including those values, and therefore, because our domain is not negative infinity to positive infinity, so we're not going to count this as a polynomial function. We have limits, and therefore, there is no degree, there is no leading term, and there is no coefficient in our minds, because we're not dealing with a polynomial function that goes from infinity to negative infinity. We're limited. All right, so let's look at what's called a power function. A power function is just in the form of f of x equals a to the xn, where a is a real number and it's not equal to 0. Also, n is greater than 0 and it's an integer, so no fractions are the n values. So you've got to be 1, 2, 3, 4, 5, and so on. Our power function, when we have an even degree, we get some information out of there. We have something that looks like y equals x to the n, where n is an even value. When n is an even value, x squared is greater than x to the 4th, is greater than x to the 6th, is greater than x to the 8th, and so on, when our x value is somewhere between 0 and 1. And this makes sense, because if we have like 1/2 squared, that's 1/4. That is certainly larger than 1/16, which is certainly larger than 1/64, which is certainly larger than 1 over 256. Because fractions raised to a power, the higher value the denominator is, the actual smaller value the whole entire thing is. Secondly, if our x is greater than 1, then our x squared is less than x to the 4th, is less than x to the 6th, is less than x to the 8th, and so on. This is what's called a hierarchy. So when x is anywhere between 0 and 1, not including 0 and 1, then as your power grows higher, the x value, the actual function gets smaller. And when your x is greater than 1, as your power grows larger, your function grows larger. We also know with our function y equals xn, doesn't matter what our n value is, it passes through -1, 1, 0, 0, and 1, 1. Okay? So it does not matter. This is for an even function. N is an even number. Then it's going to pass through -1, 1, 0, 0, and 1, 1. Those are 3 points you can immediately plot, because you know this value must go through those 3 points. As n gets larger, the graph of our x to the n gets flatter and flatter around 0, and almost vertical when x is -1 and x is +1. So as x, what this little arrow means, approaches infinity, our parabola is no longer, or our shape of our image is no longer like rounded. It's almost flat here. Almost, not quite, almost. Now let's talk about power function for an odd degree. Now, the graph, when y equals x to the n when it's odd, has the same basic shape as y equals x cubed. So it has the same basic shape as a cubic function. N also passes through, the function also passes through these 3 points. Because n is odd, it will pass through -1, -1, 0, 0, and 1, 1. Now as n gets larger, our graph gets flatter around x equals 0 and almost vertical at the -1 and 1. But instead of this kind of flat U, remember, it looks very similar to a cube function. It looks like very step-like. Now, it's not perfectly flat here, but it looks closer and closer to this format as our n grows larger and larger. And it also has a hierarchy pattern. X is greater than or equal to x cubed x is greater than x cubed is greater than x to the fifth is greater than x to the seventh, ... when x is a fraction. When x is not a fraction, it's greater than 1, then x is smaller than x cubed is smaller than x to the fifth, and it grows as the power grows. That's all it's saying, is if it is a fraction, if our x value is a fraction, as the power grows, our value actually gets smaller and smaller. The value of our function gets smaller and smaller. If our x value is greater than 1, then as our powers grow, so does the value of our f of x. So very similar to an even function. Now we want to really focus on what the end behavior of a polynomial function looks like, because we can gain a lot of information from that on how to graph if we know what these endpoints are behaving like. So are they behaving like that? Are they behaving like this? We have several ways of looking at it. So let's take a look at it. Because our polynomial function y equals f of x, it might oscillate in the middle, and it might oscillate quite significantly. But for large values of the absolute value of x, the behavior is very predictable, and it's dominated by the leading term. So even though in the middle, it might not look like x to the squaring function or the cubing function, the middle might not look like that, but the ends, it will, because it's dominated by that leading term. Okay, so here we go. I want to talk about some notation really quickly. When we have y equals f of x, as it approaches infinity, as x approaches infinity. So our function approaches positive infinity as our x value approaches positive infinity. So the values of f of x increase without bound when our x increases without bound. Next, y equals f of x approaches negative infinity as x approaches infinity. This means the value of f of x decrease without bound when x increases without bound. So our function decreases when our x increases. All right, as f of x approaches infinity, as x approaches negative infinity. That just means the values of x increase without bound when our x decreases without bound. Remember, we have to keep in mind that our domain is from negative infinity to positive infinity. So it is without bound. And when f of x approaches negative infinity, as x approaches negative infinity, that means the values of f of x decrease without bound when x decreases without bound. So I really tried to use blue for positive infinity and increasing, and red for negative infinity and decreasing, so you can kind of see how it pairs up. Now this is just talking about increasing and decreasing functions as x does something as well. We're going to utilize this to really talk about the end behavior of the polynomial, because the end behavior will go off to infinity or negative infinity depending on the function itself. Really, that comes down to 4 different possibilities. All right, in case, we're going to look at 2 cases, and I'm going to number these a little bit different just so we don't get confused about that. Okay, we have the case where our function is even, and we have the case where our function is odd. When our function is an even function, it takes on the appearance of a parabola, right? The squaring function. It might do some stuff in the middle, a little bit different, but ultimately, in case 1, we're going to have our function go off to positive infinity or go off to positive infinity. That means it rises on the left and it rises on the right. In case 2, well, it falls to negative infinity on both sides. So on the right, or on the left, it falls to a negative infinity, and on the right, it falls to negative infinity. Look where the arrows are pointing. Not that it's an increasing or decreasing function, but look at where the arrows are pointing. In the event that we have an odd function, we also have two versions. One, on the left, it falls to negative infinity, but on the right, it rises to positive infinity. And then the other case is, well, it rises to positive infinity on the left, but falls to negative infinity on the right. So when a is greater than 0, for an even function, it rises to positive infinity on both sides. When a is a negative number, then it falls to negative infinity on both sides. When a is greater than 0, it falls on the left for an odd function, but rises on the right for an odd function. And when a is less than 0 for an odd function, it rises on the left and falls on the right. Now again, this is just the direction of where the arrows are heading. This has nothing to do with if it's an increasing or decreasing function. So let's take a look at an example understanding the end behavior of a polynomial function. Let's let our polynomial function, p of x, equal 2x cubed plus 5x squared minus 7x plus 11. We know first and foremost the highest power is 3, and our degree of 3, we know it's an odd function, so we got to keep that in the back of our mind. We want to show that p of x is approximately the same as the function 2x cubed when the absolute value of x is really, really large. We're talking not just 5 or 10, we're talking very large. So let's take a look at the solution. We want to show that p of x is approximately 2x cubed. Okay, starting with our original function, p of x equals 2x cubed plus 5x squared minus 7x plus 11. I am actually going to factor out this 2x cubed. When I do that, 2x cubed comes out. I divide 5x squared by x cubed, I get 5 over x. I divide negative 7x all over x cubed, I get negative 7 all over x squared. And if I divide 11 by x cubed, I get 11 over x cubed. Now remember what we're talking about. We're talking about a very, very large absolute value of x. And if that's the case, 5 over x, negative 7 over x squared, and 11 over x cubed become very, very, very close to 0. They don't hit 0, but they're really super close to it. So this could be 5 over a million. Well, 5 over a million is very close to 0. Throw it in a calculator. It's going to be an extremely small number. Negative 7 over a million squared is really small. And 11 over a million cubed is like a 1 with, what, 18 zeros? That's incredibly close to 0. It's a really, really small number, and therefore very close to 0. So if these values are close to 0, then we really get 2 plus 0 minus 0 plus 0, which is just 2 times x cubed. Remember, it is approximately that. It's not exactly 0, but really close to those zeros. And therefore, my p of x is approximately 2x cubed. Okay? And I have shown that, well, p of x is approximately 2x cubed. And we already know that for a polynomial, this leading coefficient, or this leading term, is dominant over everything else. And this is really what it means to be dominant. All the rest will eventually kind of peter out and not make any difference in our function, and this dominant term will just take over. Okay, speaking of which, we have something that's called the leading term test. We're going to let our function a of x be this a n x to the n plus a to the n minus 1, a sub n minus 1 plus x to the n minus 1, all the way down to a sub 1 x plus a sub 0. And we want this a to the n, a sub n, oh, get my terminology right, a sub n not equal 0. Well, this a sub n, x to the n, is our leading term. And the behavior of the graph, f of x, as x goes off to infinity, or where x it goes to negative infinity, has the end behavior of one of these graphs, this leading term. If it is even, we have two cases. Now it's going to look, it's going to take on this y equals x squared, and where a sub n is greater than 0, it's going to have this kind of W squiggly effect in the middle. But look at the ends. Goes off to infinity, it rises on the left, and it rises to the right. In the middle, it's going to be some squiggly stuff. Okay? And in fact, when x is to the 4th, it actually looks like a W. When x is to the 6th, it has a couple more humps in there, and a to the 8th has a couple more humps than that. When it's y equals negative x squared, it's usually a parabola going down, but a sub n is less than 0, then again it's pointing downward. And we have some wiggly stuff in the middle. Now, this wiggly stuff will change depending on our value, our power that we have, and our a value. But again, this is for an even function. In terms of an odd function, we have two cases. Now, it takes on the shape of a cubic function, where you see where this dashed line, it could have some squigglies in there, but ultimately it takes on the shape of an x cubed. When a to the n is greater than 0, then it's going to fall on the left and rise on the right. Okay? I'm just talking about the graph itself. It doesn't necessarily have to be on the y axis. I mean, this could be shifted over here all the way, and it's just falling on the left, rising on the right. When a sub n is less than 0, it rises on the left of the function, does some squiggly stuff in the middle, and then falls on the right side of the function. So it is going to take on these characteristics because of the leading term. Is the function even and a is greater than 0, then it's going to rise both on the left and the right. If a is less than 0, it's going to fall on the left and the right. If it is an odd function and a to the end is greater than 0, then it's going to fall on the left, rise on the right. If a sub n is less than 0, then it's going to rise on the left and fall on the right. Okay, so here's what it comes down to using our notation. For case 1, let's look at case 1. As y goes to infinity, y will go to infinity as x goes to positive infinity. Y will also go to infinity as x goes to negative infinity. Let's look at case number 2. Y goes to negative infinity as x goes to negative infinity, and y goes to negative infinity as x goes to negative infinity. Now case 3, where we have an odd function. Y will go off to negative infinity as x goes to negative infinity. Those match up very nicely. Y will go to positive infinity as x goes to positive infinity. Now let's look at case 4. As y goes to positive infinity, x goes to negative infinity. As y goes to negative infinity, as x goes to positive infinity. Those are the 4 different cases. And if you notice with the even cases, if we are greater than 0, if our a sub n is greater than 0, then pretty much everything goes negative. Positive infinity is associated with positive infinity, okay, as our y value goes positive infinity. If our a sub n is negative, our y goes to negative infinity. So those kind of go nicely. Positive a's, negative a's. It's the odd functions you got to watch out for. So I say visualize it by lefting and righting. So if it's greater, then it starts as falling to negative infinity, but eventually gets to positive infinity. And when it's less than 0, it starts off in positive infinity and then goes to negative infinity. Okay, so that might be a way to memorize it or to learn it. But ultimately, if you have some notes hanging around to keep it straight, that's what the leading term test will give us, that a value in front of our leading coefficient. All right, so let's put this to the test, and let's use this leading term test to figure out what this function is going to do. So y equals f of x, and our f of x equals negative 2x cubed plus 3x plus 4. Here's our leading term, negative 2x cubed. And because our leading term has a degree of 3, number one, it's odd. So it's either going to be case 3 or 4. It is not going to be case 1 or 2 because it's an odd function. And in fact, our a value is negative. And because our a is negative, we're in case 4 circumstance. So as our x approaches negative infinity, our y goes off to infinity. Or y approaches infinity as x goes to negative infinity. And y goes to negative infinity as x goes to positive infinity. So it rises on the left and falls on the right. Rises on the left and falls on the right. So knowing that behavior, we can start kind of sketching part of our graph just by knowing its end behavior. Okay, let's talk about our real numbers of our polynomial function. And this is in terms of real zeros. So if f is a polynomial function and c is a real zero, I should say 0 there, then here's what we know. It is a real number, but it's also a 0 of the function. Then number 1, c is a 0 of f. 2, c is a function or a root of the equation f of x equals 0. 3, c is an x-intercept, in other words, c comma 0, of the graph of f. And 4, x minus c is a factor of f. So just by knowing that c is a real 0, we know all of those 4 things. So let's look at an example, finding the zeros of a polynomial. Let's find all the real zeros for each of these polynomials. First of all, f of x equals x to the 4th minus 2x cubed minus 3x squared. And g of x equals x cubed minus 2x squared plus x minus 2. Let's take a look at the first one. Okay, if I am trying to find all values that our function equals 0, I've got to set it equal to 0. And it looks like I can pull out on all 3 terms, it looks like I can pull out an x squared. So x squared times x squared minus 2x minus 3 will get me back to my function. And x squared plus, minus 2x minus 3 is factorable. So I'm going to go ahead and factor that. I get x squared times x minus 3 times x plus 1 all equals 0. I'm going to use my zero factor property to break this apart and find all my solutions. Okay, x squared equals 0, x minus 3 equals 0, x plus 1 equals 0. And if I solve each one of these, my solutions are x equals 0, x equals 3, and x equals negative 1. So those are all my real zeros of my polynomial. Let's look at our second equation. Our second function is g of x equals x cubed minus 2x squared plus x minus 2. First things first, I'm going to set it equal to 0. And because there are 4 terms, I'm going to go ahead and group them and see what I can do with it. So I'm going to group together x cubed minus 2x squared, and I'm going to group together the x minus 2. And I'm going to factor each one of these. For the first set, it looks like I can factor out an x squared, and I get x squared times x minus 2. Now, it doesn't look like I can factor anything out of x minus 2, but you can always factor out a 1, so I'm going to go ahead and factor out the 1. And it looks like they have an x minus 2 in common, so I'm going to factor that out. And I get x minus 2 times x squared plus 1 equals 0. Now I'm looking for all of the real zeros. So I'm going to break this apart. I have x squared plus 1 equals 0 and x minus 2 equals 0. And you probably say, okay, add 2 to both sides and I get x equals 2. But look what happens. I'm going to subtract 1 from both sides here, and I get x squared equals negative 1. Keeping in mind I'm looking for the real zeros, meaning a real number. And therefore, this is not a real number. So the only 0 for g of x is 2. There's only one real 0 value, and that is when x is 2. Finding zeros for a polynomial of degree of 3 or more is one of the most important problems in mathematics. It really is. I still believe there's some problems that are out there in the world that if you solve those mathematic problems, they actually pay you $1 million because these are so important problems. And a lot of them deal with polynomials of degree 3 or more. We can approximate these zeros by using what's called an intermediate value theorem. An intermediate value theorem is we're going to let a and b be two numbers with a being less than b. That's very important. A is less than b. If f is a polynomial function such that f of a, so our function evaluated at a and the function evaluated at b have opposite signs, then there must be at least one value, one number c, that's in between our a and b, for which a of c equals 0. There must be. There's got to be. Now think about that. When I evaluate a value at a and I evaluate a value at b and they have opposite signs, it could have gone from positive, this might be positive and this might be negative, or this might be negative and this must be positive. You must have crossed through 0 somewhere. And therefore, there should be some value in between a and b that when evaluated, the function evaluated at that value, it is 0. This is an intermediate value theorem. So let's use this value theorem. Let's show that this function, f of x, equals negative 2x cubed plus 4x plus 5, has a real 0 between 1 and 2. Now I'm going to show you all the steps here. I have evaluated the function at 1 and I end up getting 7. I evaluate the function at 2 and I get a negative 3. Well, remember, our function is a smooth curve. And to get from 7 to 3, I must have passed through 0. Okay, so we looked at real numbers for a polynomial, but there is actually a rule about real numbers, real zeros. When you have a polynomial function with degree of n, with real coefficients, then it has at most n real zeros. So if it's degree 3, you're not going to have more than 3 real zeros. You can have fewer, but you're not going to have more than 3. So let's figure out how many real zeros we have and find the number of distinct real numbers for a polynomial function of degree 3. So here are a couple of functions that we're going to work with. A is f of x equals x minus 1 times x plus 2 times x minus 3. Nicely that they're factored for us. G of x, x equals x plus 1 times x squared plus 1. And h of x equals x minus 3 squared times x plus 1. And let's take these one at a time. Okay, so we are going to be looking for the number of distinct real zeros. All of these have the degree of 3. So let's look up f of x. Good news is this is factored. So let's go ahead and set it equal to 0, which means we're going to set each factor to 0 and solve. Once we solve for each of these, so x minus 1 equals 0, x plus 2 equals 0, x minus 3 equals 0, we get x equals 1, x equals negative 2, and x equals 3. And therefore, f of x has the real zeros of -2, 1, and 3. It has 3 real zero values. Now let's look at our second one, g of x. G of x equals x minus 1 times x squared plus 1. Let's go ahead and set this equal to 0. We'll break off each factor and set each factor to 0. And we're going to solve each one of these. Now, subtract 1 from each side, we get x equals -1. We subtract 1 from each side, we get x squared equals -1. This is not real. It's a beautiful value, but it is not in the real numbers. So g of x only has one real zero value, and that is x equals -1. Now let's look at our third example, h of x. h of x equals x minus 3 all squared times x plus 1. Now setting this equal to 0 and solving, we end up getting x minus 3 equals 0. That equals x equals 3. And x equals -1. Now you're probably wondering, well, isn't there an x minus 3 over here too? Yeah, x minus 3 equals 0, x minus 3 equals 0, and x plus 1 equals 0. But we're looking for distinct values. We don't want repeats, or we don't need repeats. So our h of x has the real zeros of -1 and 3. So it has 2 distinct real zeros. Now when our real zero repeats like it did in the previous example, where we could have solved x minus 3 equals 0 and x minus 3 equals 0, that means we have multiplicity. Okay? Anytime that we have repeats, we're going to get some multiplicity more than 1. Okay? For example, this has real zeros at -1 and 3, but -1 happened once and -3 happened twice. So x equals -1 has a multiplicity of 1 because it happened once, but x equals 3 as a solution happened twice, so it has multiplicity of 2. So that's what multiplicity means. So let's find our zeros and their multiplicities. So we have f of x equals x squared times x plus 1 times x plus 2. So again, we're going to set this equal to 0 to find our real zeros. And I'm going to go ahead and break this x squared up as x times x. So I get x times x times x plus 1 times x minus 2. Breaking all 4 of those apart, I get x equals 2, x equals 0, x plus 1 equals 0, and x minus 2 equals 0. Solving these, I get x equals -1, x equals -2. So our zeros are -1, 0, and 2. But talking about multiplicity, x equals -1 has a multiplicity of 1. X equals 0 has a multiplicity of 2. And x equals 2 has a multiplicity of 1. So multiplicity goes along with what the solution is. And our zeros are the distinct values that force our function to equal 0. So let's change the subject just slightly. We're going to use all of these facts to start graphing things by using very special points. So recall that a turning point is a relative minimum or maximum. Minimum if the change of the function goes from decreasing to increasing. So it starts decreasing on one side. So it starts decreasing and goes increasing, that's a minimum. And if it goes from increasing to decreasing, that's a maximum. Now let's figure out turning points. There is, well, I should just put it like this. If our polynomial has a degree of n, it has at most n minus 1 turning points. Okay? if our f of x is a polynomial of degree n, then the graph itself at most has n minus 1 turning points. All right, so I'm going to go ahead and use a graphing calculator for these, and we're going to find the number of turning points. So our first function is f of x equals x to the fourth minus 7x squared minus 18. Our second graph is going to be g of x equals x cubed plus x squared minus 12x. And our third graph is going to be x cubed minus 3x squared plus 3x minus 1. Keep going. Okay, so I've pulled up my TI-84 Plus calculator app, and I'm going to put in our f of x. So it's going to be x, okay, x to the fourth, come on, my goodness. Let's see if I can clear that out. My little graphing thing is not working well. Okay, so I want x to the fourth, get out of there, minus 7x squared and minus 18. And I'm going to go ahead and graph this. If all goes well, we'll see a graph. There we go. All right, so we see that there are 3 turning points. Now I can trace this graph. Okay. So right now I'm at x equals 0 and y equals negative 18. That is a turning point. If I move my graph, my little point, I'm going down, my y value is getting down until, come on, and it looks like that is a minimum where y equals negative 30 and x equals negative 1.9. So that's a turning point. Okay, I'm going to try and move it over. Bear with me, it's a little on the slow side on my computer. That's my maximum, my local maximum there. Moving it over again. And it looks like I can go one more. Okay, and that looks like a minimum as well. So I have 3 turning points, 2 local minimum, and 1 local maximum. Okay, let's try the second function. I'm going to go back and I'm going to clear out that function. Maybe I can clear it this way. There we go. And this time it's going to be x cubed plus 2 x cubed plus x squared minus 12x. Okay, so x cubed plus x squared minus, oops, let me go back, delete that and say squared, there we go, much better, minus 12x. Used to doing it on a regular computer calculator and not this guy. Now I'm going to go ahead and graph this and see what it looks like. All right, now look at this graph and see how many turning points it has. Now you don't have to know the actual turning point values, but you can see that right here on the graph is a high point, and right here is a low point. And of course it goes increase then decrease, so that's a turning point. This goes decrease to increase, so there is a turning point as well. And in fact, it has one maximum and one minimum. Now let's go back and graph our third function. Let me clear that guy out. And we have x cubed minus 3x squared plus 3x minus 1. X cubed minus, let me start over there. Here we go. Cubed minus 3x squared plus 3x minus 1. All right, let's graph it and see what happens. Okay, so remember what a turning point is. It has to go from an increasing to decreasing or a decreasing to increasing. And in fact, nowhere along this does it change directions. It's actually increasing with negative numbers. It flattens out a little bit and then it raises, still increasing. So actually, h of x does not have any turning points. It has it is only increasing as a function and therefore no turning points. Okay, so let's get out of my graphing calculator and go back to our notes here. When we're graphing a polynomial, all of this information that we're gathering is really incredibly useful to be able to plot our graph without using a graphing calculator. All right, there's about 6 steps. One is you want to determine the end behavior. So we have 4 cases, right? That's it, 4 cases for our end behavior. Second, you want to find all the real zeros, which are the x-intercepts. Third, you want to find the y-intercept. You're going to, for the 4th step, you're going to use any symmetry if there is any. So we might have symmetry where x equals h, or we might have symmetry where y equals x. So we might have that symmetry around 0, or we might have symmetry around like the y-axis or something like that. Then we're going to determine the sign of f of x. I'll explain that in a little bit. And ultimately, using all of this information, we are going to graph, draw our graph. All right, let's sketch the graph of f of x equals negative x cubed minus 4x squared plus 4x plus 16. First of all, let's look at the degree. Let's figure out if it's an odd or even function and kind of get the sense of the end points behavior. All right, so we're degree 3, therefore it's odd, so we can only be a case 3 or 4. Either we're going to go from raising to falling or falling to raising. Our leading coefficient is -1, and therefore we're going to go from, it's a case 4 behavior, so we're going to be going off to infinity on the left, and right, we're going to go to negative infinity. So we're going to rise on the left, fall on the right. Second step, let's find all of our values, our real zeros, in other words, our x-intercepts. So here we have negative x cubed minus 4x squared plus 4x plus 16. I'm going to group it up in the first 2 terms and the second 2 terms and factor each one of these separately. We get a negative x squared out of the first set, leaving us x plus 4. I can factor out a 4 in the second set, leaving me 4 times x plus 4. They both have x plus 4 in common, so let's go ahead and factor that out. I get x plus 4 times negative x squared plus 4 equals 0. I'm going to solve each one of these for their zeros. And ultimately, I get my zeros are -4, -2, and 2. So I know that this tail, this end behavior, since that is our 0, I know that is going off to positive infinity at the -4. I know that it crosses at -2, and I know it crosses at +2 and is going in a downward situation. Now think about how we can connect these points right now. The only way to do that, where I go from way up here, come through, I go up through there, and then I come back down. That's the only way to connect those dots. But let's continue. The next one is to find our Y-intercept. So our Y-intercept is when we throw in a 0 into our function, and once you do that, you get the value of 16. So our Y-intercept is all the way at 16. This should be just a wee bit higher than where I have it, so about right there. Now the only way to get way up there is to peak and then fall back down. Now I don't know if this is my turning point, but it's somewhere around here because I've got to get from way down here, somehow way up there, and then way down here. Is there symmetry? Well, there's a test that we can run for symmetry. I'm going to figure out, well, f of x is just our function. And then I'm going to calculate f of -x. So wherever x is, I'm going to place in a -x. And if you do that, you end up with x cubed minus 4x squared minus 4x plus 16. I'm also going to do the negative of f of x. If we have the negative of our f of x, we end up getting x cubed plus 4x squared minus 4x minus 16. Now our f of x does not equal our f of -x. Therefore, there is no symmetry around the y-axis. Since our f of x does not equal our negative f of x, there is no symmetry around y equals x. So this has no symmetry. Okay, so we're going to look to determine the sign of our f of x when we're not in our zeros. Okay, so I know what my zeros are: -4, -2, 2. And I'm going to check some values before and after each of these points. So I'm just going to draw like a number line. And I have my -4, my -2, and my -2. And I just want some value before and after these values. So I've decided to select, well, -5 is on the left of -4. -3 is between -4 and -2. 0 is between -2 and 2. And then I need one more to the right of 2, so I'm just going to select 3. You could have chosen any value. You could have chosen 1. As long as it's in between -2 and 2, I don't care what value you check. Any of these values will definitely give me the sign of f of x. So I'm going to calculate what of my f at that value that I've selected. So in my test value of -5, my test value of -3, my test value of 0, and my test value of 3. I'm going to plug it into my function, and you can see all my work here. I get the value of 21. So when x is -5, I get the value of 21. When x is -3, I get the value of -5. When x is 0, I get the value of 16. And when x is 3, I get the value of -35. Now this tells me when I put in a -5, I get a positive value out. That means anything on this side, the sign of my graph is going to be positive. When I plugged in a -3, I got a -5 out of it. That means this portion is negative. When I plug in a 0, I get a positive 16, which means everything in this region is positive. And when I plugged in a 3, I got -35, and therefore everything past 2 is going to be negative. Now think about this. Positive is above the x-axis. Negative is below the x-axis. Again, positive is above the x-axis, and negative is below the x-axis. So I actually have 4 more points that I can plot. At this point, I am ready to sketch my graph. I've not only got these 4 points, but I also have my zeros that I can plot as well. So here we go. Negative 521 is up here. Negative 3, 5 is down here. Here my zeros are already on the graph. 0, 16, remember that's my y-intercept. I have another x-intercept. And remember, way down here is 3, negative 35. And everything below that is going to be negative. So I know, looking at my end behavior, I was going off to infinity. The only way I could get back to my zeros was to hit a turning point. I have some turning point up here, and I come back down. This is the sketch of my graph. Now I'm going to go ahead and plug this graph into my graphing calculator. So where'd my graphing calculator go? Here we go. And let me get the actual, here we go. I'm going to clear that out. And I have x cubed minus 4x squared plus 4x plus 16. And let's see how close we are to what we plotted and what the graphing calculator will plot. So negative x cubed minus 4x squared. Oh, darn it. I forget. I'm still in the exponent, so I need to clear this all out. Get out of there. There we go. Let's try that again. Negative x cubed. I'm used to having a mouse. Sorry about that. Get out of there. I've got minus 4x squared plus 4x, and we have a plus 16. All right, and let's graph this and see what happens. Very similar to how we plotted it by using those special points and knowing the end behaviors of our graph. So very similar. Let's go through one more example before wrapping up this lecture. Let's look at the volume of a wine barrel. The volume of a cylinder with the radius of r and the height of h is given by this formula. We have the volume equals pi r squared h. Now, we're going to change this up a little bit because the picture of our barrel is actually, we're going to place a rod in the barrel. And the length of this rod is x. And we know the height of this barrel is 2 radius. In other words, the diameter of the barrel is 2r. We know the height, aka the length of our barrel, we're going to say z plus z. In other words, 2 z's. The reason why we're going to do this is because we're going to try and measure the volume based on the length of this rod. So we know this length right here, this h, is worth 2 z's. So we can rewrite our formula as in volume equals 2 pi r squared z. 2 from the 2z. Okay. But this length of the rod, this x, we can get from the Pythagorean theorem. So x squared plus 2r squared plus z squared is the Pythagorean theorem. And I want to solve this. I want to get x squared equals 4r squared plus z squared. All right, we're getting there. We're going to express this volume as a function of x. So I need every other variable to go away. I need r's to go away, and I need z's to go away. And the only variable I want on the right-hand side is x's. So we've got to do some finagling here. So we're going to assume the height divided by the diameter is going to be 2z divided by 2r. In other words, z over r. We're going to assume that this ratio is the square root of 2. That's an assumption we're making, that z over r is the square root of 2. Now here's our solution. By making this assumption, we can actually solve this and only get x's in our formula. So let's start with our formula as we have it right now with z's and r's. We have the volume equals 2 pi r squared z. We know that z over r is the square root of 2. We know that x squared equals 4r squared plus z squared. Well, let's go ahead and divide everything by r squared. We get x squared over r squared equals 4r squared over r squared plus z squared over r squared. Now the r squares disappear on this 4. So we get x squared over r squared equals 4 plus, well, that's z over r all squared. But remember that assumption we made about z over r, this ratio is the square root of 2? So we have x squared over r squared equals 4 plus the square root of 2 squared. Well, the square root of 2 squared is 2. So 4 plus 2 is really 6. So we know x squared over r squared equals 6. And therefore we can solve it for r squared. R squared equals x squared over 6. Now remember, we're trying to get x in, this r go away and the z goes away. We now know that r squared is x squared over 6, so we can replace that. All right. Now, we know r is, the square root of r is x over r, the square root of 6. And because a radius cannot be less than 0, we know it's positive, so it's okay to do this. All right, so we pretty much got rid of that r squared. We know what r squared is, but we don't know what the z is. So let's go ahead and use the fact that z over r equals the square root of 2. Well, that means z equals r times the square root of 2. We know what r is. That was x over the square root of 6. Now I'm going to get rid of this square root of 6 down in the denominator. I really don't like it down there. Your book does it a little bit differently, but I'm going to get rid of this square root of 6 down below by multiplying both top and bottom by the square root of 6. Doing that, I get z equals x times the square root of 3 over 3. I know what z is, I know what r squared is. Let's plug it into our formula and see what we get. So our original volume was, or our second version of our volume is 2 pi r squared z. Our r squared is x squared over 6. Our z is x times the square root of 3 all over 3. This 2 and this 6 can be reduced. And I get v equals pi times x cubed times the square root of 3 all over 3. But this pi times square root of 3 over 3, you can actually plug it into your calculator and you get approximately 0.6046. So we can replace all of these values with this 0.6046, and therefore our volume, when based on the length of the rod, is going to be 0.6046 times x cubed. We got rid of all the radius, we got rid of all the height. We're now figuring out if our rod is 2, then we would say 2 cubed times this. Whatever length of our rod is in the barrel, we can figure out the volume of our barrel now just by using the length of a rod. All right, that's it for this lecture. Until next time, be seeing you.